Okay, good afternoon, everyone. Let's get started. So today we're going to talk about linear regression again, but it's going to be, instead of using just one variable to predict, we're going to use several variables to predict. So this is called multiple linear regression, and last unit, when we use only one, it's called simple linear regression. So there's going to be a lot of similarities between what we did before and now. So we'll see that coming up. So the demo or the practical problem we're trying to solve through this lecture is predicting the progression of diabetes. So diabetes is an important disease. Kills a lot of people. So the question is, can we predict the progression of the disease from biometrics like age, sex, body mass index, blood pressure, and the results of a blood test? So we're going to be using a kind of a famous data set, the diabetes data set. So this data set has 442 samples, and it has 10 attributes or features. These ones, so you have like age in years, sex, body mass index, various other things you can get from a blood test. And then there's one other piece of the data set, which is the target, which is a quantitative measure of the disease progression 1 year after the baseline, 1 year after the initial state of the disease was measured. Okay, so this data set happens to be part of the machine learning library sklearn. sklearn is pretty much the main package we're going to be using all throughout the semester. It contains many methods for machine learning. It also contains a few built-in data sets, some of the most common ones people look at for tutorial type purposes. So loading this data set is very easy. It has the same kind of interface that we saw for the first demo. So you basically load this directly like this, and then you get a structure where there's a data and a target structure, just like last time. And if we look at the data structure, we'll call that X, and you look at its shape, that's a way of basically finding its dimensions in NumPy. You find that it has 442 samples, like we said, and 10 attributes or features. Okay, so how are we going to represent our data then? So we saw last unit already, we saw a pandas data frame which showed that was the automobile data set, and we had sort of like an array, two-dimensional array, where as you went down from one row to the next row, those are different samples, and as you went from one column to the next column, those are different features or attributes. So that's exactly how we're going to represent our data mathematically. We're going to take all of our feature values and put them together into this X matrix. So if you look closely here, there are n different rows in this. So n is the index of the last row. So that's going to be, like I said, it's going to be the variable we use all throughout the term to represent the number of samples in our data set. But now, different from the last unit, we have multiple features. We have a total of D of them, and we're going to be consistent with D. That's going to be, all throughout the semester, the variable we use for the number of features. So here you can see we have D columns. So this is a matrix here that has n rows and D columns. Now, it often is helpful to come up with a name for each row. So each row would contain the features for a particular data sample. So let's say we're talking about the ith row, then it would go from xi1 to xid. We're going to call this xi transpose. So xi transpose will be the ith row of our data set. So another way to write this matrix is like this, where each one of these is a row, and you're just stacking the rows on top of each other. Okay, and then our targets look just like before. This is a column vector with n samples. For each feature vector, we have a corresponding target scalar. Okay, so that's how we're going to represent our data, again, all throughout the term. And now let's talk about how we do the linear model now that we have multiple features. Oh, it looks like okay. I didn't mean to upload the version to my notes that had I was gonna write this out by hand, but so here it's already filled in. But you can see this is the linear model. We have, just like before, we have an intercept term, right? But then for each feature, we also have a slope term. So before it looked like that. We had intercept and one slope. Now we have multiple slopes. Each one of these features gets its own slope. But otherwise, it's the same principle as we saw before. Okay, is everybody good with this? Okay, great. So, so let's talk a little bit more about how we're going to. Actually, I'm going to. Let's talk a little bit more about how we're going to work with this data, and we'll do it two different ways. The first way is a bit more direct, not as interpretable, and then second, we'll use statistics and we'll get something that's more interpretable. Okay, so here's what we get if we rewrite our model, but now I'm talking about the ith sample. So because I'm talking about the ith sample of the data set, you can see we have subscripts I on all the x's and the y. So, so this basically says, if you tell me what these coefficients beta are, these are the things I have to design. Then, given some feature values from my data set, I can make a prediction of the target in my data set, y hat I. And if things are going well, then this prediction here will be approximately equal to the true yi. So this is the true one. The one with the hat is the predicted one. Okay, so so we defined this X matrix before that contained all of the training feature values. Now we're going to do something just slightly different. We're going to append a first column of ones onto that matrix. So this part here, this submatrix is the X, and I'm putting an underline under it to indicate that that's bold. So that's the X we saw before, but now we also have the column of ones. So the question now is, does anybody know why we're adding this column of ones? Why is that convenient? So let me just ask, is Anutam Srinivasan here? Yeah. So why do you think we? The intercept? Yeah. So can you explain it just a little bit more? Like, why is that for the intercept?
Is it because the intercept isn't changing at all based on the variables?
Yeah. Okay. So basically, what I was looking for is that the reason we're adding the ones here is that so we can easily do a multiplication of this quantity by this quantity. Because this intercept here, you can see if I multiply this matrix times this vector, what happens, the way matrix vector multiplication works is that this will multiply all the terms in the first column, beta 1 will multiply all the terms in the second column, and so on until beta d will multiply all these terms here, right? And so that's why we're adding it, is so we can do an easy multiplication between this quantity and this quantity, where the beta 0 will be multiplied by 1, so that it gives us this term in every sample. So given that, what do you think we'll get for, how can we express y hat, which is the vector of all these predictions here stacked on top of each other? How can we express y hat in terms of the A matrix and the beta vector? So is Shengping Wu here? Yeah, so what do you think? A times beta, exactly. So this enables us, this enables us to write y hat the vector is just the A matrix times a beta vector. Okay, so I want to make sure that's clear to everyone. Is that making sense? Okay, so now we have a really compact way of describing things that doesn't require us to write things out with a summation. That's nice. It will allow us to, it's just a more compact way of doing things, and it will allow us to get a simple solution for beta that we'll derive later today. Okay, so then let's suppose that I got my training data, which is my x and y or my a and y, and I somehow figured out a way of determining beta. So I somehow did this training, and now I know beta, and now I want to actually put my model into practice. So now I'm not talking about training data anymore. Someone's going to give me a new set of features from something I've never seen before, and I'll call those x. And I want to make a prediction. From those features, I want to predict what is the target. And I don't really know what the target is, right? Now I'm actually putting my model into practice. So how would I write my my prediction, y hat, based on this new feature vector x? This is not in the training data. So how could I write this y hat in terms of the beta and x?
Could you transpose your vector x and then insert a 1 at the beginning?
Exactly.
Multiply it by beta.
Exactly. I can do it this way. So I'm essentially creating what looks like one of these rows by taking the 1 and then appending on the right of it x transpose, which would be like the remainder of these. And then I can just multiply by beta, and that will give me a single scalar, which is my prediction of the target for that set of features x. Is that making sense? Okay, great. So are there any questions at all? Okay, so that's just, yes.
Can you repeat that why we added the column of 1?
Well, we're trying to set up a matrix vector multiply that essentially accomplishes what we see in this model. So in this model, we see that the beta 1 through beta d are multiplying the x's, but then we see that there's just a beta 0 that's standing alone, not multiplying anything. And we started with this matrix of x values, but that matrix of x values tells us essentially how we want to use that to multiply these betas, but then the question is, how do I deal with this term? So it's convenient to stack all our betas together into one vector, including beta 0. But if I do that, then I have d plus 1 terms here, but this has only d columns. So I'm adding that extra column of 1s because I'm going to just multiply the beta 0 with 1 to get that intercept term.
And what happens to beta 1 to beta d?
Oh, well, so beta 0 multiplies the first column. Beta 1 multiplies the second column, so you can see it's doing this job, right? Beta 2 multiplies the next one all the way, and finally beta d multiplies the last one, doing that. Yep. Yeah, so all this sort of linear algebra stuff is so important, and that's why I assigned that homework, and I want you to take it seriously, and really, you'll get practice as we go through the lectures. You'll see a lot of those concepts here in the lectures, but all that stuff is super important, being able to just kind of look at things and sort of read it fluently, like a language. Okay, but I think everyone has the concept now, right? Okay, great. So let's now address, now that we sort of have the mathematics defined, we need to figure out how can we determine the optimal beta coefficients. Okay, so before we start even saying how we determine the optimal coefficient, we have to say, well, what do we even mean by optimal? What is it that we want to minimize to define optimality? And so we're going to do the same thing as in the last unit, which is to try to minimize the residual sum of squares. So it's identical to last time. In fact, almost everything on this page is identical to a page you saw in the last pack of notes. The only real difference now, as we know, is instead of one term here, we have D terms. There's D features. But the RSS definition is identical. It's just the sum over our n training samples of the true target minus our prediction of that true target. And in this case, the prediction is here. The only other thing that's a little different is that the picture we had before, we had a line in 2 dimensions, and now we can expand it by one more dimension. So let's say that this is beta 1, sorry, not beta 1. That is x1 and x2. Those are, let's say I just had 2 features, d equals 2. If d equals 2, then I have 2 features. And now I would be creating a regression plane. So how many degrees of freedom do we have in a plane? Let's see, is Xiaolun Tong here? Yeah, so how many degrees of freedom do I have in a plane? How many ways can I adjust it? What do you think? Just imagine all the different ways you can turn it and move it. Not sure? Okay, so basically we can move it 3 ways, right? Like imagine you have a plane. You could tilt it along this axis, that's 1. You could tilt it along this axis, that's 2. And then you can just raise it up and down independently of those tilts. So there's really 3 different ways we can move this plane around. And that's not a surprise because we actually have 3 parameters here. We'd have beta 0, beta 1, beta 2, right? So beta 0 is still going to be our intercept. Beta 1 is going to be how things are tilted. It's a little hard to see it in 3 dimensions, but like, you know, if you tilt it along this dimension, that would be beta 1. And if you tilt it along this other dimension, that would be beta 2. And beta 0 is up and down. So you can see now that by adjusting these, in this case, 3 beta coefficients, you can move that plane around anywhere you want. And that plane is our prediction, that represents our prediction, because essentially, to do a prediction, we would be given a pair of x1, x2, and given that pair, you could just look up to see, you know, where on the plane is that, and that tells you, this should say y hat here. That tells you the y hat. Well, we can leave it at y. Let me emphasize that the plane, this plane is the y hat. Yes?
I'm a little confused by the degrees of freedom, so you can only tilt it in one axis and then just move it in every other?
So we can tilt it along the x1 axis without tilting it at all along the x2 axis. That would be what beta 1 does. It adjusts the slope in the x1 direction.
And because we have 2 features, we have.
That's right. And beta 2 adjusts the slope in the x2 direction alone, and then beta 0 is the height.
Why isn't there also another tilt? Like, why does it go up and down and not like side to side or?
Oh, if you move, so
it's
plane is like
infinite plane.
infinite, right?
Okay.
Right. So if we move it side to side,
Gotcha.
it's the
Doesn't
same
matter.
plane.
Okay.
Yeah, that's a good question. Okay. So so that's sort of like just visually you can see what we're trying to do here. And now, just like in the last unit, we can, if we like, we can call these epsilon I, right? That was the prediction error. That was the difference between y hat I and yi. And so where on this plot would we find that prediction error? So let's see, is E on U here? Yes, so where on the plot would I see the prediction error? Epsilon I. So the prediction error are just those red lines. So if you remember, so y hat is the plane. The actual data are these black dots. And then the epsilon I would actually be this little line here. And as I move the plane around, it changes the length of the lines, right? As I move it. And so if I move the plane like really high up, then all the lines would be pointing down and they'd be very long. If I move the plane down, the lines get shorter. If I move it just right in the middle, I can minimize the sum squared, the average squared length of the line. That's exactly what we're trying to minimize. Okay, so is it clear kind of visually what we're trying to do? All right, so then what we have to do next is figure out mathematically, like how do we actually do this where we can give it to a computer and have it do the work for us. Okay, so kind of going in that direction, we're going to define a concept from linear algebra, which is going to help us rewrite this RSS in a slightly more compact way. So this is the RSS that we had on the previous page. It's just the sum of the squared differences. And this might look familiar to some of you. If you think about the norm of a vector, a norm is basically in linear algebra, a norm is just a way of measuring the length of a vector. And there's actually different ways to measure lengths of vectors. The one we're most commonly used to using is the Euclidean norm, which is just like the straight line distance between 2 points. But we'll talk about other norms later, like if I'm a taxi driver in Manhattan and not a crow flying, and if I want to get from one place to another, I can't take the direct line. I have to drive down one block, turn, drive down another block. So that's actually called the L1 norm. But this norm is just as the crow flies, direct line between 2 points, and that's called the Euclidean norm or the L2 norm. So that's what we call the usual norm in this space. And when you use the usual norm, you don't even really have to say which norm you're using. So this is how we denote a norm with those two double bars on the vector. You could optionally write this as x with a little 2 under here. And the 2 is reminding us that we're using this L2 norm. But because this is the kind of standard or default norm, people often just leave off the 2, and then you just say, oh, it's the usual one, it's L2. Question?
Is there a difference between the magnitude of a vector and the norm of it?
Well, technically speaking, there is no such thing as a magnitude of a vector in linear algebra. Vectors are objects within a vector space, and if you want to measure their length, that's called the norm. The magnitude is really just a scalar. If you have a scalar quantity or a complex valued scalar, and you want to know, like, the absolute size of it, that's the magnitude. But does that make sense? Yeah, it's just kind of a terminology thing. So, I mean, actually, we're not going to talk about it this way, but vector spaces are very generic spaces. You can have vector spaces of functions where the elements in the space are functions. And then you want to say, like, what's the norm of this function? That's kind of like if this function is some sort of vector, and you can still visualize it as like we do here, like how long is that function? So now you need to define an appropriate norm for that function. Maybe it's the integral of the function squared over the real line, something like that. So that's just kind of linear algebra in general. In this course, we're going to be focusing on finite dimensional vector spaces, so just arrays of numbers of finite length. That's the kind of vectors we're going to be using. And in that case, it's just the Euclidean norm, which is just summing the elements, summing the squared elements. That's the usual norm. Okay, but there is this square root. Notice that. So if I want to get something of this form, what do I have to do to a norm? I just have to square it. Okay. So given that, now you can hopefully see, if I want to express this is a sum of squared entries in some vector, then I can do that with a norm, or actually a squared norm, as just the vector version here, which is the y vector minus the y hat vector. Take the norm of that, the Euclidean norm in this case, and square it. So it's just kind of a notational thing. But I guess it's conceptual too. It's like we're creating the true vector, the predicted vector, subtracting them to get the error vector, and then looking at the squared norm to say, that's the thing I want to minimize. Okay. And Yeah.
Why here? Why hat is predicted value? But
Exactly.
Why here?
Y without the hat is our data. This is coming from our data set.
Actual data.
The actual data.
Actual data.
Yes, the actual data. Right. And in fact, for Y hat, we can expand that. We derived on the previous page, I think, that it was the A matrix times the beta vector. So now it's maybe more clear. RSS is directly written as a function of the parameters beta that we want to design. Okay, so this is a very common way to express RSS, something we'll see a lot throughout the term. Okay, any questions? Anything here? Okay, great. So if we step back, then we might notice that we're following this general recipe that we saw in the last unit, where we propose a model with some parameters. In this case, we're using a linear model with multiple features. We're gathering data. The data in this case contains feature vectors instead of scalars, as well as targets, which right now are going to be scalars. In some later unit, we'll actually extend them to vectors too, but for now, let's just keep them scalar. And a loss function, which in this case is the sum of the squared prediction errors. And our objective now is to figure out what are the betas in this model that minimize this RSS, or equivalently minimize this squared Euclidean norm. Okay. So now we have a slide that's very similar to what we saw in the last unit again. We're going to take the same approach as we did before. We're going to exploit the fact that when you're trying to minimize a function of different parameters, and that function is continuous so that you can take derivatives, then at any minima, you will find that all the derivatives in all the different directions, they simultaneously go to 0. And that's what we used in the last unit. We had two betas, beta 0, beta 1. Now we're doing exactly the same thing, but we have d plus 1 betas, from beta 0 all the way up to beta d. Conceptually, it's the same, it's just we have more coefficients. But now I can just give you a little bit more of the math, so we can understand maybe a little bit more about how this is quadratic and so on. So this is what we derive our RSS as. Now, one important property of the norm is if I have, let's say I have a quantity like, I'll just call it A, the squared norm of A. How can I write that without a norm in terms of A itself? So let's see, is Jagadish Yedla here? Yeah. So how do I write this squared norm but without the norm? Can you think of a way? It involves a transpose somewhere? Yeah, A transpose A. That's right. A transpose A. Exactly. So this is a super important thing, and maybe one way to visualize this, I often find it helps to write some or draw some little pictures. So if this is A transpose, the first one, and this is A, now the way that matrix multiplication works is you take the first times the first, plus the second times the second, plus the third times the third, and so on, right? And when you do that, you can see you will get like A1 squared plus A2 squared, and so on. And that gives us this quantity that we saw on the previous page as the squared norm. So it sort of helps to visualize maybe why this is true. But okay, so given this important property, we can take this, we can expand it as y minus A beta transpose y minus A beta. And now we can expand this quadratic into 4 terms. The first times the first, so that's going to be y transpose y here. And then we're going to have, there's going to be 2 cross products. So let me actually show you what they are individually. So we have, we're going to have y transpose A beta. So I got that y transpose A beta, and that's actually, there's a minus sign. And then we also have another one, which is this A beta transpose Y. Right, so that's A beta quantity transpose Y. Now, okay, we can rewrite the second one. So another important thing, if you have a product of matrices, in this case A times beta, and you transpose that product, then you get the first one transposed times the second one. So it's important that you reverse the order. Right, that's an important thing. So let's do that. So, oops. So we'll replace this with beta transpose A transpose Y. But now there's actually something else. So it might initially look like these are different things, but they're not different things. So let's say why they're not. So everything here is a scalar, right? The norm is a scalar. This is a scalar. This is a scalar. This is a scalar. If we want to visualize these terms, maybe I could do it this way. I have Y transpose, which is a row vector. A is a matrix. Beta is column vector. When you do those multiplications, it comes out as scalar, right? So if you think about the way transpose works, transpose is like you're kind of flipping the rows and columns on a matrix. So what happens if you transpose a scalar?
It's the same.
Nothing, right? So since these are both scalars, that means I can transpose them without changing them. And now you can see if you transpose this first one, you switch the order, you put a transpose in each one, you get beta transpose times A transpose times Y. Right? So they are the same. So it's just, instead of writing them as two separate things, let's just write 2 times the common thing. Okay, so I'm not going to spend always this much time on the linear algebra, but just because we're at the beginning, I'll spend a little bit more time on it. So finally, at the end of the day, we have the RSS can be decomposed into 3 terms. And now that you look at it, you can see there's one term which is a constant with respect to beta. There's another term that's linear with respect to beta. And there's a third term that's quadratic with respect to beta. It has beta appears twice. So overall, this is a quadratic in beta. If you would go and multiply out all of the individual terms, you could do that with a double summation, or maybe even a triple summation. You would eventually find that this term has all these combinations of different betas, like a beta I times a beta j, but you would only ever have 2 betas multiplying each other, never like beta I times beta j times beta k. So this is just quadratic. And when you have this quadratic function and you plot it in the beta space, you end up getting something that looks like this. It's some 2-dimensional parabola, hyperparabola. And it turns out there's different ways that parabola could manifest, right? It could be curved up, it could be curved down, it could be like a trough. But it turns out that the way that RSS is set up, it can never be curved down. That's impossible. And that's to say that so curvature is actually the second derivative. Slope is the first derivative, curvature is the second derivative. And one way to parameterize the curvature of this function of multiple parameters is the Hessian. So the Hessian, so we talked about the gradient last time. Gradient is a vector of partial derivatives like this. The Hessian is a matrix of these double partial derivatives. d beta j, d beta k. So all the different elements in this are different values of j and k. And if this matrix is positive semi-definite, this is called the Hessian. This one. If this is positive semi-definite, then you know that it's curved up, or at least it's never curved down. And we're going to get more into this later in the course, but if you don't know what positive semi-definite is, it's not a big deal. I'm not going to get into it right now. But under those conditions, essentially we know that if I find the place where the gradients go to 0, then I know that that's the minimum. And that's what we used last unit. That's what we're using again. And the second picture is the same as what we saw before. These little arrows tell us the gradient, where it's pointing, and how, basically the norm, how steep is the surface. The steeper it is, the gradient has a larger norm. The arrow gets longer in this plot, quiver plot. Okay, so this is just a bit of defending why we're going to try to set the gradient vector to 0, and then use that to solve for the betas that are the optimal solution. Okay, any questions on this? Okay, so let's do the least squares solution now, and we'll just do this from first principles. So over here, we have the definition that we've seen before. In this unit, y hat takes this form. So this is a slightly different way of writing it than we've seen. So what we saw before is we saw the y hat vector is the A matrix times the beta vector. Now essentially we're looking at the ith entry in that y hat vector. So let me draw a little picture again. So here's the y hat vector. There's the matrix A, is the beta vector. And so now let's say I'm looking at a particular entry here. And so that, to get that, I'm going to take this row and multiply that times beta. Right? Does that make sense? All these other terms in the A matrix do not impact this ith entry here. This is the ith entry counting down. So from there, hopefully you can see that in order to write that y hat I can use this sum here. So I'm just going to go, so j is going to be indexing this way. I'm going to start with j equals 0, that term times the beta 0 term, plus the next j times the next beta term, or the next a times the next beta term, and so on. And so doing this vector multiply, I can get y hat this way. Is that pretty clear where that sum comes from? Okay. And this is just sort of a definition. We're defining using the little a's. This is like you take that big matrix and you extract the ith row and jth column. That's what I mean by that square bracket. Just extract that one element, scalar element, no bolding, and that's what this is. Okay, great. So that's just setting up a little bit of notation. And in the last unit, we saw something very similar. It's just we didn't write it with the AIJs. So just like the last unit, we're going to do this. We're going to take the gradient with respect to beta j, and we're going to use the chain rule. So I want to take the gradient of this with respect to beta j, or let's write it out. Let's write this as, there's a sum over j of aij beta j. Okay, so when we do the chain rule, we can move this gradient through the sum and focus on this term. So then we're going to get 2 times yi minus y hat I times the derivative with respect to j of yi minus y hat I. So here's the 2, here's that, and then let's look at what is the derivative of this. Let me be really careful, and let me use a different variable. I'm going to use j prime. Okay. So the reason I'm doing that is the following. So the variable j has a very special meaning here. I've chosen j to say I want to take the derivative with respect to the jth element of beta. Okay, so j has a meaning. I cannot redefine j by expanding this into a sum involving j. because the j that I'm using that for clashes with this j that's already been defined. You can't use the same variable to mean two different things. So I can use any variable I want as long as it's not I and j. So I'm going to use j prime to say, yeah, it's like j, but it's just a different j. I could have used k or something else, but I just used j prime. So now that we have that straightened out, so if I want to do this d y hat I d beta j, how do I do that? So here's my y hat I. So as you can see, this is a sum of a bunch of different terms. I'll write it out explicitly. We're going to have a I0 beta 0 plus a I1 beta 1 plus dot 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 all the way up to a ID beta d. And I want to take the partial derivative with respect to the jth one. So the jth one is just some arbitrary one. Maybe it's here. So do you see what I'm going to get when I take the partial derivative with respect to the jth element in the sum? Anybody? Yeah.
Only the coefficient Aij.
Aij, exactly. Only that one. All the other terms in the sum have nothing to do with beta j, so they fall away. So it all boils down to the coefficient in front of the single term that depends on beta j. It's just going to be Aij. So that is where this comes from here. Okay. So again, let me just do it again. So we're starting with this. We want to take the gradient with respect to beta j. We're going to use the chain rule. So what that means is the 2 is going to come down. It's going to turn into 1. So that's where the 2 comes from. Then we're going to have this term. And then we're going to have the gradient of the thing we're squaring. And that's this d. Well, okay, so the gradient of this whole thing. So that's the gradient of yi with respect to beta j is 0 because yi as a data does not depend on the parameter I'm trying to tune. And then I have the gradient of this with respect to beta j. So I can maybe put a minus there. And we just said that this is going to be minus aij. And that argument comes from expanding y hat I into this sum, but being careful not to reuse j because I'm using it here. Just call it anything else like j prime. And then realize when you take the derivative of this sum with respect to the jth term, you just figure out which is the jth term, and you forget all the others. You focus on that term, and now it's just a nice simple derivative. It's linear in beta j, so it's just the constant in front of the beta j. Aij. Okay. Is that pretty clear? Okay. So that's how we got this expression. Hopefully everybody's good with that. And now we're going to do some more linear algebra gymnastics, which is we want to go backwards and take this sum and write this sum actually in terms of matrices and vectors. So that's why I have all these problems on the homework and quiz going both ways. Take matrices and vectors, write them as sums. Take sums, write them as matrices and vectors. So in this case, I have these y quantities. I know that I have vectors constructed with those y's. I have this aij, and I know I have a matrix that involves those. So how do I write this sum in terms of matrices and vectors? So it has this form. Let me draw a little picture again, maybe to make this clear. So imagine that I have this aij matrix, and I have a vector now of y terms. This is like my y minus y hat vector. And I want to do what's written in this sum. So I'm freezing, let's say, okay, so I'm freezing the value of j. J is fixed, but you can see there's many different i's. So, and the y's are actually indexed by the i's. So I can draw maybe a little arrow going down this way to say that's where the i's are going down. They're going down this vector of y minus y hat. So as I go down that vector, I increases. For this to be a valid matrix multiply, I also have to then have I going across the columns of this other matrix. Right? So now I'm wondering, how do I make a matrix full of the aij's, where across the columns I have I, and that means that across the rows I must have j, right? Because that's the only other direction to go. So is this the original aij matrix, or is it something a little different? It's the transposed one. Because in the original aij matrix, when you look at this A matrix, full of aij's, you have it going this way. So to make this thing work out over here, I just needed to transpose this. I needed to flip where the I and the J was. And now I have something that works out. So basically, okay, was there a question back there? Okay. So it might be easier to see how you go from here to here. And with practice, you can figure out easily how to go the other way. But so I have this A transpose matrix here. I have this vector. And so if I want to look at the jth entry, so overall this is a vector, right? If I want to look at the jth entry in that vector, then I'm going to be looking at the jth row of this matrix times this vector. And the jth row of this guy here is going to be constructed of aij's, where j is fixed, but then the I is changing from 1 to n. So that's how we're writing this sum in terms of this matrix vector multiply. So there was definitely a bunch of homework problems on this, quiz problems, quiz 0, but we're going to be using this stuff quite a bit. This is probably the hardest point of linear algebra, is going in this direction, from what I've noticed. But it just takes practice. It's not really difficult, it's just something you got to practice. I find these little pictures to be very helpful, at least for me. Okay, question?
Is I usually default for going downwards?
So I'm using I to default the data index, the index on the samples in our data set. So whether it goes, to the right or, columns or rows really depends on what we're doing with it. So in this case, it's happening to go across the rows. Now, in terms of just like, if you read like some linear algebra textbook and they say there's a matrix and let's look at elements in the matrix, they might use ij, they might use jk, they might use kl. But yeah, it's probably like the row one alphabetically is before the column. So m, n, j, k. That's most common, but it's not necessary. As long as you define it and it's clear, it's fine.
Okay, thank you.
Okay. Okay, so going back up a little bit then, what we derived is we have this expression for this partial derivative. We wrote it with the sum. We also wrote it with a vector, and we're saying if you extract the jth element of this vector, then that equals this. And we can go even one further step. We can resubstitute in our y hat if we want, which we know is a beta. And so now we have this RSS derivative expressed in terms of things we know, data, and the things we're trying to design, which is beta. Okay, so the reason it's convenient to write it in terms of this vector is we actually need this to be 0 for all values of j, not just a particular one, but all of them, which means we need this whole vector to be 0 at all of its indices. So basically that means we can just say, if this happens at all j, this is our design equation. We want to find the beta that accomplishes this. So can I somehow solve for the beta that's doing this? Because this is the beta that sets all the gradients to 0. We're going to call this the least squares beta. Okay, so basically setting, yeah. So let me just write this. This is for all j going from 0 all the way to d. Okay, so that is where we got this equation. And the rest is, next step is not too difficult. You just take A transpose Y, leave that on this side, and then you take A transpose A beta, you move that to the other side. And now we have the unknowns on the left side, and we have the unknowns multiplied by this matrix. And you've probably seen this in linear algebra classes, but if you want to solve for betas here, this is a square matrix. If it's invertible, you can invert it. Essentially, you can think of it as multiplying both sides of this equation by A transpose A inverse. So if it's invertible, it cancels this out. You get beta least squares. And on the right side, you get A transpose A inverse times A transpose Y. At the end of the day now, as you see, we came up with a nice, concise expression for the least squares parameters that works for any number of features, D. Could be 1,000,000 features, could be 2. But this is the equation that tells us exactly how to solve for these coefficients. And you can see it takes a bit of horsepower to do this when there's a lot, because you have to invert a matrix. And matrix inversion is something that the complexity grows cubically in the dimensions of the matrix. So, when this thing is thousands, it takes a little time to actually do this. Okay, so, but the point is we now have an expression for our least squares coefficients. Any questions about how we got? Yes.
Okay, forgive me if I missed something, but how did we get beta transformed to LS? Unless I'm mistaken?
So it's just like, are you asking like where this came from?
Yes.
It's just I just added it there because this is the specific thing that happens when this gradient equals 0. That happens at the least squares solution.
Oh, it is.
Yeah, that's just the least squares solution. Okay. Any other questions? Yes.
Can that be further simplified expandation?
It's a good question. We will write it a different way. Whether it's simpler, I think it's more interpretable the way we're going to write it, but it's, I would say this is like the simplest in terms of just number of terms. Yeah, but it's not very interpretable. So that's kind of an issue because inside this A matrix, we have like all of our features X, but then we also have the ones, and it's just like, at least to me, it's not exactly clear, if I double the features, like double the size of all my features, what's going to happen to this, So, I mean, okay, so actually that is visible, but yeah, I think it can be, we can make it more interpretable, and that's what we're going to do next. Yeah.
So before we had beta naught and beta 1 and beta 2, those were scalar values, and here beta ls is a vector, so it's like
Yes.
an infinite number of betas,
It's containing all those betas, finite number.
finite number.
Yeah, not infinite.
Up to.
Up to D, yeah, D
Yeah,
plus
up to
1.
D, yeah.
D plus 1, because you start counting at 0, so you go up to D plus 1. Yes. Okay, great. Okay, so one other comment about this invertibility. So to get this to be invertible, there are some things we need. So if the number of samples in our data set is less than the number of features we're trying to, or number of beta coefficients we're trying to design, n is less than D, this will not be invertible. And so we can't really, it doesn't make sense to write this down because this thing does not actually exist. So we're going to talk about that situation later. It's not very common. In machine learning, you typically have many more data points than you do features. But it does happen once in a while, and we will see it on some of our labs. So it is important to talk about. We'll talk about it later. Okay. All right, any other questions on this page? Okay, so in terms of measuring how well our predictor is doing, It's exactly like what we did in the last unit. In fact, this slide is a exact copy of the slide in the last unit. We use a normalized version of RSS. Essentially, we take our RSS, we divide by n to get rid of its dependence on data set size. We divide by the variance on the target's y to get rid of the dependence on the absolute size of your targets. And then to use sort of a standard terminology, r squared, you subtract that normalized thing from 1. And you get this r squared, and we talked about how r squared equals 1 means the prediction is perfect. In this case, it would mean all your data fits perfectly on a plane, or a hyperplane of dimension d. R squared equals 0 means it's really bad. That's the worst that least squares can ever do, is get r squared equals 0. And if you're doing r squared less than 0, it means you're doing even worse. So if you're coding something in the lab and you're trying to code least squares and you're getting a negative RSS, what does that mean? It means you made a mistake somewhere, right? It's impossible. Okay, so that's a good thing for debugging. Okay, great. So I think that's a pretty good place to stop for today. But are there any last questions on anything? Okay, if you have any questions, you can ask them after class. And next time we'll come up with a more interpretable version of that beta vector. See you guys on Friday.